Today on the bench, a UHF duplexer. Duplexer? What is a duplexer for? And why do we need to align it on two different frequencies? Let's have a look exactly into that. Welcome to TRX Bench. Alright, and here we have it. So the first what you might notice is that we really have here two frequencies mentioned on our duplexer. But first of all, you might wonder what we need a device like this for. So maybe you are more familiar with a device like this. So this is also a duplexer, but this one here is used if you have a radio, for instance a Kenwood TM733. So that is a dual bender, and it has two individually antenna connectors at its backside. So one is for VHF and the other is for UHF. And if you're only using one antenna, so we have this diamond antennas like the X30 or so, which can be used for VHF and UHF frequencies, and it is only one antenna. And in this case you need something like this. So you really need to put one output from the radio here to VHF and the other output from the radio to the UHF, and then you connect your, for instance, Diamond X30 or X50. So there are different models on the market with different gains, and then you are really able to use both sides of the radio. And of course there are radios on the market which has already a duplexer inside the radio, but there are, as I said, radios which have both available at your backside of your radio. And it is certainly easy to understand that if you really put both outputs simply together without a duplexer, then if you transmit with one side or with the other side, then the full energy of your transmitter stage will go back into your receiver pass of the other band as well. And that is very simple to understand. This will simply destroy your front end of your radio. So you really need to separate these both frequencies. So when you transmit on, let me say here, the UHF band, right, then you want the full output power going to your antenna, so very clear. But on the other hand, you do not want to get any of your output power back into your receiver pass, where it would destroy simply your radio. And this is what a duplexer is basically doing. And what we have here is not so much different to what we have discussed earlier, but this unit here is for repeater use. And you can see it here a little bit. So we have two different frequencies on a repeater. You may know that we are using offsets, and the offset is different in the different countries. So here you can see that we have an offset of 7.6 megahertz, which is a typical offset for 70 centimeter here in my area. And so this here was used for an repeater, and you see the repeater frequencies, of course. And now we need to realign this duplexer as it will be used for a new repeater, and therefore the frequency have changed. So we need to align it, and you already see that we have here different alignment screws for our filter blocks. And so we have here a little bit the same what we have seen on the small duplexer for a radio output. So we have here our antenna connector. So this duplexer will be used with a repeater where we also only use one antenna, and of course we will have a receiver, and we will have a transmitter, and the transmitter and the receiver have an offset of this 7.6 megahertz. And of course it is basically exactly the same story. So imagine we have here connected our antenna, and let's imagine we have finally connected our transmitter maybe here to this port, right? And now we transmit into our duplexer, and if the duplexer is not able to separate our transmitter signal from our receiver signal, then that again would mean that the whole power of our transmitter would directly go back into our receiver, right? And that, as I already said, would destroy your receiver. And therefore, exactly what we had with the other one, we need to separate our transmitter path from our receiver path, but we want to have here our one and only antenna. That's it. And therefore, first of all, let's see how it looks like if we sweep a duplexer like this. And if you see the graph, then you may even better understand what we are really talking about. And of course, before I forget it, it is absolutely important that our ports are really fulfilling our 50 ohm impedance. So of course we need to have our 50 ohm impedance either for our transmitter and the receiver, and of course as well for our antenna. So that is important that we have 50 ohm, and that means we are really looking for a low SWR if we are really transmitting into our duplexer and if we have connected our antenna. So that is for sure. And of course this really needs a certain level of attenuation to the other port. That is, as I already described it, not to have full power of our transmitter, and therefore there are some requirements which a duplexer needs to fulfill. And additional to that, of course, we are connecting a transmitter, and this duplexer, for instance, is built for a RF power handling of 25 watt RF power. And you see there are some additional requirements a duplexer need to deliver. Okay, so I have prepared our network analyzer, And now let's see what the graph is telling us. So I've already pre-adjust here the settings a little bit, and I explain it in a second. So you see down here, I have set here our center frequency to 434 megahertz, and I have a span of 30 megahertz. So from here to there, that is 30 megahertz. And first of all, I have connected here, you can see it down here. So I have connected our high frequency or our high filter first to our analyzer. So you see here is what we have connected, and this here is the graph we are getting out of it. Okay, and now we are really wondering what the graph is telling us, and maybe it will help a little bit if we look for the frequencies. And on the sticker we have here on our duplexer, we see that the high frequency for the moment, what is aligned here to our duplexer is 438.1 megahertz. So therefore let's simply use here a marker, and let me set the marker to 438 100, which is approximately here. All right, so you see here 438, and the exactly frequency would be 438.1, which would be a little bit more in this direction. But anyways, this is our first marker, and the second marker we want to put here onto this, yeah, let me call it notch, because there is the highest attenuation. So therefore let's use, that was a little bit stupid, so let's do it again, because I need my second marker, of course. And let's take the second marker, and we just put our second marker here down to our deepest point of our filter. And what you see first of all is that we have here something around minus 72 dB, which means this is really a very good filter depth. But what does that all mean? So once again, on our sticker we have this frequency as the wanted frequency, and this is the frequency of our second pass. So that is our low frequency. Okay, so 430/500 is exactly our low frequency, and what you can see here, it is at minus 70 dB, and our high frequency is at minus 1.3 dB. And this here is our zero line, right? So that means if I would now transmit on 438/100, all right, then all my energy would really be able to go to the antenna port, and we would get our full power to the antenna. But our energy should not go into the receiver pass of our receiver, of course. And we know the second frequency on a repeater is in our case the offset of 7.6 megahertz, and that is then of course our 430.5. And what you see here, 430.5 is attenuated by 70 dB, and that means that the output power cannot hurt our receiver, and that means that is exactly what we want. Okay, but so far we only have tested here our first port, and we have not tested here our low configuration, right? And once again, I mean, it is wrong way around, but I hope you can read it anyways. So once again, these are the frequencies we have talked about and we have seen on the graphs, and that is where we put our markers, right? So we are really talking about these both frequencies. Okay, but now let's check our second port, and therefore let's simply disable our update for this graph, and let's use the second trace, which is now in red, of course, and let's activate it, which we have done now. And now you see both graphs, the yellow one and the red one, are one over the other. But now what we are doing, we are changing here to the second port, and let's see what will happen then. Okay, and you see I have now here changed the port, so now the low port is connected, and we can have a look how that looks like now on the screen. Aha, and now you see our red graph, and let's explore it a little bit. So now I just put exactly the markers on the wanted and unwanted frequencies. So first of all, I'm now placing a new marker. Let's see, marker 3 on trace 2. All right, and here we are. So first of all, we place our marker 3 on our transmitter frequency, which is 438.100. And what you see, of course, is that these both markers are matching, and that is clear. The frequency where one side of our duplexer should be able to have a low attenuation is of course the side of the second filter set where we have our highest attenuation, right? And therefore the same will now be here with marker 4. If I put now the marker here on this notch, then you will see here's our marker 4, and it is on the wrong trace. I want to have it on trace 2. And when we go here now on our marker 4 into the notch, you see that it is exactly on 431. It should be 100, but therefore our resolution is not good enough. So therefore you see this was the one where we wanted to have our full power present, and we wanted to have the other side attenuated. And now Oh, I have here our marker 3 on the wrong, no, marker, what was it, marker 1, I believe, on trace 1, marker 1, is that right? No, and is it marker 2? Something is going wrong. 1 second, please. Okay, sorry for that. Now I have all my markers on the right place. So now we have exactly the situation as described before. So if we are here watching our red graph, which is on 430, so marker 3 for 3500, so that is now our transmitter frequency, right? And we are transmitting, and you see if we are getting here to our receiver frequency, then we have here our huge attenuation from over 86 dB, and that means it will definitely not hurt our receiver. And if our yellow graph would be the transmitter, then it is exactly the same. We would transmit on 438/100, which is of course here in my country not the case, because we have minus 7.6 megahertz offset. And as I said, the offsets are different in different countries. So and you will see the new offset which we have to align is different as well. So therefore a duplexer always have to work on both sides, on both ports. So low and high must be both must be able to attenuate always the unwanted side, and that is what we have on the yellow side as well. So this is the wanted frequency and this is the unwanted, and there we have the highest attenuation. So you see over the years, so I've seen the date code here for the alignment was in 2011, so 6 years ago. So here the red graph, you see it is still really at the deepest point, and on the yellow one you see it could be done a little bit better, so that we really get the lowest notch here, and maybe it is possible to also align here our wanted frequency a little bit better, because you see we have a loss of 1.3 dB here, and well, on here on marker 3, which is the other port, you see it is only 0.82. So that is the insertion loss, and so we can simply say both. The insertion and of course the attenuation is better on the red port than on the yellow. Okay, and that are our new frequencies for the new repeater. So that are the given frequencies from our radio authority here, and yeah, therefore we have to align our duplexer to this new frequencies, and you see the delta is with the new frequencies 9.4 megahertz. So let's go for it, and let's try if we are able to align these both frequencies. And of course, following exactly the same idea from wanted and unwanted frequency. and we will see later on when we connect the radio to this duplexer how it then look like, and how it really hangs together and how it works. I mean, under a real condition, and that is what we want to simulate here in the lab as well. Maybe in a second part, I'm not so sure by now, but we will see. And as we discussed earlier, these three cavities are now responsible for our high frequency. So therefore we have to undo here this locker nuts that we will be able to adjust our filters here. And yeah, so therefore let's do that first. Yeah, and that is relatively easy. I undo it like so, and now this one is already open, and of course we do exactly the same here with that one, and of course we have to do it here with come on, we have to do here exactly the same. And that means now we have really all three nuts loose, and we can start our alignment process. Yeah, and let's see what will happen if I start turning here my adjustments. So let's see how that looks like on our screen, that we get an idea of what we are doing here. Alright, so I have again here our graph, and you have seen I have undone here my nuts, and now when I start here turning, yeah, you can see it very easily that we are simply able here to change the graph. And yeah, so that is now what we need to do. We need to trim this to the wanted frequency. Okay, and what I've done first, I placed here my markers, because that are approximately the frequencies where we want to have our highest attenuation, or on the other hand our pass, or our lowest attenuation. And therefore you see I have dialed in for the wanted frequency, so lowest attenuation, for 39.8625, and I've dialed in here for 39.500, so that is very close to what we want. And our second marker is set to for 30.4625, and it is set to 430.500, so that is, oops, you can't see it, so that is here then our point where we want to have our notch. And now I really start to align it, and really try to do my best to get the best attenuation to that point. And of course that will definitely take a while, so let me do it off camera, as really it will take a while. So we will get it managed somehow, and I will then get back to you, and I will show you the result. But you see, I'm already getting closer to our wanted frequencies, and let me a little bit play with it, that we have a nice responding graph here, or responding filter what we have here set our markers to. Alright, and here it is, and it looks pretty nice. So you see our wanted frequency is very little attenuated, and here our wanted frequency at our notch has really a very deep filter response. So we are, as you can see, below 90 dB. So that is awesome, no problem whatsoever. And now we gonna reconfigure here our filter. So that means we swap now our tracking generator over to our receiver side. Okay, and our yellow graph is now representing our receiver side, and you see here at that marker we need our notch, so that is not the best we need to have. So now I start adjusting here, and yeah, let's see how we will be able to get it done. And again, so that will take a while, and therefore let's check, and then I will be back when I have a good response. Okay, and have a look. So that is now our receive response, filter response. And well, the receive side might be even more important, because we want really the filter to cut off our transmitter. I mean, on the transmitter response, okay, so the red graph, so we really want to have a low attenuation for our transmitter frequency, and of course we want to notch out here the receiver frequency. But just if you look from the receiver, then you may understand that you really want the receiver side filter to cut off here our transmitter, because if the receiver gets its receiving signal, it is for sure that you need a low attenuation. But now, if you transmit with your radio, you really want the receiver to completely cut off the transmitter power. And what you see here, so that is really awesome. We are really peaking here the 100 dB, and that is really a very good filter response. And we really should be able to completely cut off our transmitter without losing the output signal, because on the red graph our attenuation for our wanted transmitter frequency is excellent, and now on the receiver side we have really the most possible attenuation. And the specs are telling us that our filter here, our duplexer, should be better than 70 dB, and 70 dB would be this line here. All right, and you see how much we even deeper than our 70 dB line, which is again here. So that means we really have an excellent receiver, an excellent filter response, both on transmit and receive side of our filter. So that is awesome. Alright, so we have seen our filter setting is just fine. So the duplexer is working on its required frequencies, so that is no problem. But our next step is we need to make sure that the SWR, or the return loss, is good in both directions. So for the moment in time, I am here with my mini vector network analyzer on the antenna port, and I have here a load, a 50 ohm load, a dummy load at our low port. So that is now representing our, let me say, our receiver configuration, because from the antenna you get the signal, and then on the low side will be our receiver. I mean, these filters are bidirectional, so you can really do it both ways, but let's do it how it will be in reality, that we are 100% sure that everything is just fine. And in this configuration, so that means receiver configuration, right? We need a low SWR on 430 something. So let's check if we really have a low SWR on that frequency. Okay, and that is our return loss graph. And what you basically see is, here is our 430 something megahertz, and you see here is really the lowest SWR, or the highest return loss. So the line down here is minus 17.63 dB, or it is, I don't know if you can read it here on the screen, but it is 1.3 to 1, which is not too bad, but let's zoom it in a little bit. Yeah, that is the same graph zoomed in a little bit, and now you can see that the SWR, which is here the blue line, is at our frequency, our receiver frequency, 430.4 something megahertz, is 1.3 to 1, which is not too bad, and our return loss, so that is the corresponding value, is at minus 17.59 dB at our required frequency. So that is not too bad, but let's double check if we are in specs. Okay, and here are our specs here from the unit, and let's zoom in a little bit, and I hope you can see it. SWR should be below 1.5 to 1, and our test is telling us that our SWR is at 1.3 to 1. So that means it is fully in spec, and 1.3 to 1 is just fine, no problem whatsoever. Okay, now we are really doing exactly the same, but in transmitter configuration. So here at the high port will be connected our radio, our transmitter, when the repeater station is installed. Okay, so we are then transmitting here into the high port, and we have here at our antenna port, of course, our dummy load, because the energy will be right into our antenna and right up into the air. So that is the configuration, and let's check how it looks like on the graph. Okay, and that is our transmitter graph, and you see here where we have our markers. So that is transmitter frequency, and you see we are not meeting here our deepest SWR, which is here somewhere around 438, whatever. But anyways, so our transmitter SWR is still in spec, so it's 1.5, it is 1.55 to 1. So let's call that is in specs. So nothing to complain. So that is still a very good SWR. And that means now we are sure that in all the needed configurations our duplexer is doing its job, and that is just fine. Alright, and I have here the radio, which will be the transmitter in the new repeater station. So this radio will really be our transmitter, and as we already know, that means that this radio will transmit on 439.8625 megahertz. So let's check both, if it is on frequency, and secondly, what is the output power this radio is putting out. Okay, so let's check the figures. So you will see here the output power, and here you will see the frequency. And now, yeah, let me press the PTT. And what we see is the radio is putting out 8.4 watt, and we are on 439.862. 862, and then it should be 583.6. Oh well, it's close enough, so no problem. So obviously, yeah, radio is still cold, so maybe that it will get a little bit better when it is getting warm. But anyways, so we see it is definitely the right frequency where we had our duplexer set to, so no problem. And we have 8.3 watt output power, and yeah, as we already discussed many times, this 8.3 watt should not hurt our receiver pass, and therefore we were adjusting our filters to get the right cutoff. Now let's simply connect here our radio to our duplexer, and let's see how it works together with our duplexer. Alright, and our specs are telling us that the power loss in the past is approximately 1 dB or a little bit lower, and we have seen that we were around 1 dB, and of course it is not only here our duplexer itself, so we have a little bit loss on the wires, a little bit loss here on the connectors, and so forth and so forth. So if we had approximately 8.5 watt, so that is what we tested, and that is if we reduce it on approximately 1.5 dB, so with all losses calculated together, then we should get an output of somewhere around 6.5 watt something. Yeah, let's see if that is really true. Okay, so let's see what our output power will be, and it is approximately 6.3, and I set approximately around 6.5, so that is working fine. So all the losses we have calculated together, so that makes sense, and now we can be sure that this configuration is just fine. Okay, and our next important point is what will be the power isolation between our transmitter port and our receiver port. So we have discussed it a lot of times right now. So we have seen that the filter depth was around 90 dB something. So that means with our 6 point something watt we are putting out, we should see a signal approximately 90 dB under our 6 point something watt. And 6.3 watt, for instance, is 38 dBm, so plus 38 dBm, and then of course we have to calculate our 90 dB attenuation, so that means 38 dBm minus 90 dB means our readable power here on that port should be around minus, if I calculate it quite right, it is minus 52 dBm. So let's say our power, which we can see here at our receiver port with our transmitter frequency, should be around minus 50 dBm. Okay? Okay, and now the moment of truth. So, of course, I go and press here our PTT once again, and let's see what we have. And awesome. That is really awesome. So see what we have. So this is here now our signal, our transmitter signal at the receiver port, right? And you see it is approximately minus 50, 51. So very, very close to what we have calculated, what we are allowed to see at our receiver port. And that means everything is just fine. So our duplexer is working as it should, and it really is protecting now our receiver path, and that is really fine. I mean, minus 50 dBm. That means, of course, that a receiver can read this signal, but you know, it can't get hurt, because minus 50 dBm is S9 plus 20, or maybe we are here on UHF, so we have other or different figures. So minus 93 dBm is S9. So okay, so that is a bit higher, but it can't hurt our receiver, and that is exactly what we need. But what you need to know as well is, of course, this minus 50 dBm is a signal strength which would a receiver see, but don't forget, our receiver is tuned to 430.4625 megahertz, which means we have a frequency offset, so a delta of 9.4 megahertz. So the receiver will not recognize the transmitter signal, because it is simply switched to another receiver frequency. But anyways, if this signal, this minus 50 dBm would be too strong, then even the receiver is not tuned to this frequency, it still would hurt the front end and would definitely destroy it. So now everything is just fine. Alright, so that's it for today. I hope you got some new informations. I hope you got some background and some additional tips how it hangs together and how it works. I hope you enjoyed it a little bit, and thanks for watching. If you like it, please give me a big thumb up for the video, and catch you next time. Bye!